Now what the theorem says, Cayley-Hamilton theorem says, is that a square matrix A satisfies its own characteristic equation. Okay, we have already seen that A minus lambda I equal to 0, which can be written as A11 minus lambda, A12, A13, A21, A22 minus lambda, A23, and A31, A32, A33 minus lambda. The determinant is equal to 0. And this can be written as minus 1 to the power of n, where n is the order of the matrix, lambda n to the power of n plus p1 lambda n minus 1 plus p2 lambda n minus 2 and so on, plus pn lambda to the power of 0, which is 1, is equal to 0. Or in other words, we can also write it as minus 1. We can take it to the other side, it disappears. So we are left with lambda n plus p1 lambda n minus 1 plus p2 lambda n minus 2 and so on up to pn is equal to 0. This is called the polynomial representation. Okay, so as per the theorem, if we substitute lambda with the matrix itself, the equation stands true. That is a to the power of n plus p1 n to the a to the power of n minus 1 plus p2 a to the power of n minus 2 and so on up to pn is equal to 0. Here 0 stands for the 0 matrix, or we can write it as phi of A equal to 0. Because remember, this can be written as phi of lambda. Okay. So now let's prove this. So remember, elements of matrix A minus lambda I are at most of degree 1 in lambda. So here if you notice, the maximum of power of lambda is 1k. When we replace them by their cofactor, then they would be at most of n minus 1 degree. So the way to think of it is that when we evaluate this determinant, what will we end up with is, when we multiply these two, we get lambda square, and when we multiply with this, we get lambda cube, right? But if we focus only on the cofactors, then lambda times lambda square, that's all is left. So it would be of n minus 1 degree. So here it was 3 by 3, so degree was 3 in lambda. If we take only the cofactors, then it will be of degree 2, that is 3 minus 1. So therefore, adjoint of A minus lambda I can be expressed as a matrix polynomial in lambda. That is, adjoint of A minus lambda I is equal to B naught lambda n minus 1 plus B naught lambda n minus 2 plus and so on up to Bn minus 1. And in the previous session, we have already looked at, we arrived at the adjoint of A minus lambda I, right? And that matrix we split it based on the power of lambda to arrive at this expression. So here B0, B1, B2 and so on up to Bn minus 1 are all n minus 1 by n minus 1 matrices whose elements are functions of Aij summation. right? Because remember, when we are looking at, we are using Aij to arrive at capital Aij, whose elements are all functions of Aij. Now, we have already seen this in our previous session. So, if you are not very clear, please look at adjoint of A here. So, here if you notice, we have arrived at this. Now, this was very specific to a 3 by 3 matrix, right? This was for a 3 by 3. So, similarly, we can generalize this, which is what I have done here. So, this is the generalized form of that equation. Okay, so we know A times adjoint of A. Remember, one of the properties of adjoint is equal to the determinant of A times I, identity matrix. So therefore, if instead of A, we take A minus lambda I times adjoint of A minus lambda I, we get determinant of A minus lambda I times I. Yes. Now this implies A minus lambda I. Now adjoint of A minus lambda I, we can write it as a matrix polynomial. So B naught lambda n minus 1 plus B1 lambda n minus 2 plus and so on up to Bn minus 1 lambda to the power of 0, which is 1, is equal to, and this again we have seen here, where is it? This. So determinant can be expressed as a polynomial. So this will become minus 1 to the power of n lambda to the power of n plus P1 lambda n minus 1 plus and so on up to Pn times the identity matrix. Okay, now comes the tricky part. Now let's expand it. We get A B naught lambda n minus 1 minus B naught lambda n. B naught I becomes B naught, because remember B naught, B1, B2 are all matrices, plus A B1 lambda n minus 2 minus B1 lambda n minus 1 plus AB2 lambda n minus 3 minus B2 lambda n minus 2 and so on up to ABn minus 1 minus Bn minus 1 lambda. Yes, this is equal to minus 1 to the power of n times lambda n plus P1 lambda n minus 1 plus P2 lambda n minus 2 and so on up to Pn times. Now you will notice both right hands, this is an equation. So right hand side, left hand side are equal. So that means the coefficient of the like powers should be equal. So comparing coefficients of like powers, what do we get? We get minus B naught is equal to, B naught is for lambda to the power of n. Lambda to the power of n is here. So minus 1 to the power of n I, because I is there here. Okay. Similarly, AB naught minus B1. This is for lambda n minus 1. So AB naught, and here B1 is also n minus 1. See here. So AB naught minus B1 is equal to minus 1 to the power of n P1 lambda to the power of n minus 1. So P1 I. Okay, similarly AB1 minus B2, this is n minus 2. N minus 2 is AB1. AB1 minus B2 n minus 2 is equal to minus 1 to the power of n and P2 lambda We don't have to write the lambda I. And this will go on till we reach a b n minus 1 is equal to minus 1 to the power of n p n I. Okay. Now you have to be aware of what do we have to achieve. We have to achieve this a to the power of n, a to the power of n minus 1 and so on. So here do we have a to the power of n? No. Here we don't have a to the power of n. So multiply this with a to the power of n. Similarly, here we don't have a to the power of n minus 1. So multiply this by a to the power of n minus 1. Multiply this by a to the power of n minus 2. And so on till we reach here where we multiply it with a to the power of n minus n. Okay. So now what we need to do is see what happens after we multiply it. Let's multiply. This becomes minus a to the power of n b naught is equal to minus 1 to the power of n a to the power of n I. Similarly, a to the power of 1 is already there. N minus 1 gives us n b naught minus a to the power of n minus 1 b1 is equal to minus 1 to the power of, I don't need to write for everything, minus 1 to p1 minus 1 to the power of n p1 a to the power of n minus 1 times I. Okay, then we have a to the power of n minus 2 plus 1. A is already there, so this will become n minus 1 b1 minus a n minus 2 b2 is equal to minus 1 to the power of n p2 a n minus 2 times I. Okay, this will go on till we reach a times a to the power of 0, that is 1. So a b n minus 1 is equal to minus 1 to the power of n, and we have p n and I. Now let's look at the left hand side. What happens? This and this gets cancelled. This and this gets cancelled. This and the term here would get cancelled. A term here and this will get cancelled. So on the left hand side, it will all become 0. And on the other side, and all these cancellations will happen because we are adding. Okay, so now minus 1 to the power of n is common to all of them, and I is also common, so that will take it on the other side. So here we end up with a n plus p1 a n minus 1 plus p2 a times n minus 2 and so on up to pn I is common to all of them. Or if we rearrange this gets cancelled if we take it to the other side, whether it is plus or minus. So we end up with a to the power of n plus p1 a to the power of n minus 1 plus p2 a to the power of n minus 2 plus and so on up to plus pni. See, when we multiply I with all of these, no changes. But here we don't have a matrix. So pni is equal to 0. This is nothing but the statement or the characteristic equation of a minus lambda I, where lambda has been replaced with the matrix A itself. So here a to the power of n, a to the power of n minus 1, a to the power of n minus 2 and so on are replacements of lambda. So therefore Cayley-Hamilton theorem is proved. That's it for now. Bye.